Okay. Well, from the way this video is going to be titled, you probably have already guessed what it is that's odd about this clock, and that is that it runs backwards. You can see this second hand turning backwards. This clock was, it's a synchronous clock. It runs off AC 60 hertz power. Your typical wall clock, usually you'd find it in a kitchen or something. This one was made, it's a General Electric, oh, what does it say on the back panel here? Model looks like 2H116, volts 115, cycles 60. General Electric Company, what is that? I can't quite read it. This is Masonite. This is the back panel from this clock. Made in USA. Well, duh. But a lot of these clocks used a very similar motor and gear cases. And it didn't take long for people to realize this simple hack that you could do on these clocks to make them run backwards. They're still accurate with this mod. They do still keep time. It's just a synchronous, it's got a synchronous motor, and it's still synchronized to the 60 hertz AC line to keep time. But it just runs in the opposite direction. I have seen guys that going as far as to actually renumber the dial face. You know, just as an artwork, you know, oddball stuff. We used to do it as pranks to people. And it's especially annoying to them if there's no sweep second hand where they can see that it's going backwards. And they set the time, and they come back later and it's way off. Oh, well, actually it's keeping time, but it just looks differently than it is supposed to. So, I just put this way to make this short clip, just to show how it was done and how it can be done very simply. For this clock and many others, the only tool you need to do this is a screwdriver, and the mod is completely reversible. And I'm going to stall this while I prepare for that, and show you how to undo it, which is the reverse of doing it. It's so simple and stupid. Just about anybody with a screwdriver and a little bit of moxie can get in there and make these do this. So back in flash. Okay. First, I think a brief word about these motors. This is unplugged, of course. There are exposed terminals in here. Don't need it plugged in right now anyhow. But a word about these motors. These things, back in those days, they were everywhere. Clock radios often sported these, or some variation of it. Wall clocks certainly did. These are the ones that ran off of regular, here in the United States, 60 hertz current. Notice on this thing, there's the coil. This is just coils of wire in there, and that's what's is supplied with 60 hertz, 120 volts, 115 volts, whatever. Magnetizes this laminated iron core assembly. But here, right here, this thing and this thing, those are copper. Very, very electrically conductive. They are not at all magnetically conductive, where the core here, the magnetic core, is very magnetically conductive, but designed so that it is minimally electrically conductive. That's why it has laminations. They don't want the iron is conductive, of course, but they don't want it to be conductive here, so they divide it into sections that are insulated from one another to prevent currents from flowing, electrical currents from flowing in places they don't want it. That causes inefficiency. But what they do is they exploit the shorted turn thing here and here. These are called shades. This is a shaded pole motor. They're very common in clocks of this era, and also phonograph motors, the drive motors for phonographs, because they're very closely, the rotation of the armatures in these types of motors is very closely tied to the frequency of the current and not so much the voltage. Variations in voltage cause no, within limits, cause no variation in the RPM of this armature. That's what you want in a clock. That's what you want in a record player, so that the speed you want is the speed you get, and it is controlled by the frequency of the input. So something you could do with this clock is you could put 100 hertz into it. Well, that'll make it run faster. You could put 40 in. That'll make it run slower. Don't recommend doing that for various reasons, but making them run backwards is stupid simple with most of these wall clocks. The clock radios get a little more complicated because things might be in the way. There's not as much room. But all I did to make this run backwards was take this armature out, or I'm sorry, this stator out, flip it over, and put it back in. That's it. Which reorients these two shades here. Those shorted turns, what they do is they cause a delay, which, I don't know, you probably cannot see it, but in this stator core, the iron part, there's a gap here and down here. So these become two separate poles just because of that gap. One side of this coil, the other side of this coil. The magnetic flux from this coil, 60 hertz, pulsing back and forth, going down and presenting itself to this armature. We'll get into that momentarily. But what these shorted turns do, notice this is a split. The core splits right here. So you got one side going here, the other side going here. These cause a delay in the magnetic field fluctuations, which causes a rotating magnetic field here. These do pass current, and they do get warm, and for that reason these motors are not efficient. But they are very good at maintaining a constant RPM, speed of rotation, that is very much locked into the 60 hertz, regardless of the voltage, but within limits. But it's very much locked in to that. The other thing, the positioning of these will also determine which direction the armature inside of here turns or rotates. So with just let's see, it was 2 screws to take the back panel off, okay, and it's 2 screws, fasteners, to get this motor off of the clock. You don't have to remove the whole mechanism from the clock case or its face. Yeah, that's fine. And that's what it looks like. This has a couple of screws, fasteners, a couple of spacers, plastic spacers, and there's the motor. See what it looks like, hopefully. Now, all I did to make this go backwards was to take the gear case and armature assembly out of the field pieces, the stator core, and put it in the other side. And this thing, it's not glued in or anything. It's just kind of captured in there when the assembly is put together. And this can spin, but now this will cause this motor to run in the opposite, turn in the opposite direction. It's as simple as that. I'll put it back together. I probably won't waste your time with showing how that's done. It's the opposite of what I just did. These things, you can see this. You can get a clear shot of that. Two connections to this coil, but these are two shorted turns, one on this side, one on this side, and that's going to determine the direction of rotation of the armature in here. It's also going to make it very much synchronized. That's why they call these synchronous motors, with the AC frequency coming in. These things. You'll notice this looks copper. It's because it is. It is copper. The reason being, it had to be a non-magnetic conducting material. Copper is, of course, very electrically conductive, but the angles at which this is presenting to the magnetic field produced here, current does not flow through this copper. These are also later models of these were the casing was made of aluminum. I think the top here is looks like nickel-plated steel. Not sure. It's sealed. There's a pretty stout, robust crimp around here. I've seen on the aluminum ones. I've seen ones that they just use an adhesive of some sort, like a rubber cement or something, something like that. These have oil in them. Not a lot. These are meant to be positioned this way, with the gear at the top, because that's a place, if you did it this way, the oil could ooze out of this. And it does anyway, because these get warm, and some of the oil may, components of the oil may vaporize in there. And so some of that probably does escape through this bearing. But otherwise, these are sealed, and they last a long time. Jeez, I remember cutting these things open as a kid, and putting a drill, chucking this in a drill, and getting about a zillion RPM until the thing flew apart. What's in here? The larger part of this is the gear case. The reduction. The armature is a tiny. You would be surprised if you've never opened one of these up. Usually in these, it's a very, very thin shaft, and with two very thin discs on it that are cut. They have either holes in them, or they look like they're sort of like stampings. A little bit difficult to describe what's in there, or how it looks. I could draw it, but oh, good Lord! Buy one of these at a yard sale. Cut the motor open. You'll see. That's what I did. And so I'm gonna cut this and stitch it, and I'll reassemble this back the way it was, and just show you a clock that works like it's supposed to, or the way most people expect it to. There. Okay, all back together like it's supposed to be, and I'm not going to do too much. I'm going to clean off the outside of the case a little bit. I'm not going to touch the dial, the dial in there. That in this appears to be cardboard, or whatever. The chances are you try to clean that, you just wipe the numbers clean off of it. And don't want to do that. This has some sentimental value to me. And here's back, so it looks like put together. I think my dad cut the cord off of this and put the shorter one on. This, as I said, or maybe as I said, was a kitchen clock for as long as I can remember. And I'm old. And this thing was in service, oh gosh, somewhere in 1962, maybe, 3, till, oh gosh, around 2001. Constant service, never had a trouble. And I inherited it, and it's been sitting idle for, since 2001 or so. And so I decided, well, somehow the subject of this came up, and I thought, well, go ahead and add to the fun, and show what you can do with some of these old beasts. Hey, hope you enjoyed. See ya.